welcome to the mathematics class, and I am Sandeep Jaiswal. This video is for class 10th students. We will continue our first chapter, that is real numbers. Let us start with Theorem 1.3 given in your NCERT textbook. Let P be a prime number if P divides A square, then P divides A, where A is a positive integer. This theorem has come one time in your examination, and also this theorem is helpful in solving the other questions. As we have seen in fundamental theorem of arithmetic that any composite number can be written as product of primes, so we will apply it for A and we will find the prime factors of A. Let us now prove the theorem. First of all, let the prime factorization of A be as follows. A equals to P1 into P2 into P3 up to Pn, where P1, P2, P3 and Pn are primes, not necessarily distinct. Therefore, A square is equal to P1 into P2 into P3 into Pn, again in another bracket P1 into P2 into P3 into Pn. Since P is a factor of A square, as it is given that P divides A square, then by fundamental theorem of arithmetic, P is 1 among P1, P2, P3 and Pn. As fundamental theorem of arithmetic says that A square cannot have any other factor other than P1, P2, P3 and Pn, therefore P should be 1 among these P1, P2, P3 and Pn. But as our assumptions, P1, P2, P3, Pn are the factors of A, that is A is equal to P1 into P3 into Pn. Therefore, P is a factor of A, thus P divides A, hence our theorem is proved. Let us now prove the next theorem, that is theorem 1.4. Prove that root 2 is irrational. We will prove this theorem using the contradiction method. In contradiction method, we just assume opposite of the fact given in the question. So now let us see the proof. Let root 2 be a rational number. Then root 2 can be written in the form of P by Q. So take root 2 is equal to P by Q, where P and Q are integers and co-primes. Here we have used the term co-prime. Co-prime means the numbers which do not have any common factor. So P and Q do not have any common factor according to our assumption. Now on squaring both sides of the equation, we get 2 is equal to P square by Q square, or the equation can be written as 2Q square equals to P square. So we can say here that 2 is a factor of P square. Now since 2 is a factor of P square, therefore 2 is a factor of P by fundamental theorem of arithmetic. So we can write P equals to 2C, where C is any integer, and 2 is a factor of P. On squaring both sides of the above equation, we get P square equals to 4C square. Now using equation 1, that is P square equals to 2Q square, we can write this equation as 2Q square equals to 4C square. Or solving this equation, we get Q square equals to 2C square. So from this equation we conclude that 2 is a factor of Q square. Then by fundamental theorem of arithmetic, we get 2 is a factor of Q. Thus what we see here, that 2 is a factor of both P and Q, which is a contradiction to our assumption that P and Q are co-prime. So our assumption is wrong, thus root 2 is irrational. This proves our theorem. Here we have one more similar type of question. Prove that 5 minus root 3 is irrational. This question will also be proved by contradiction method. So let us start the proof. Let 5 minus root 3 be a rational number. Then 5 minus root 3 can be written in the form of P by Q, where P and Q are integers and co-prime. Or the equation can be written as 5 minus P by Q equals to root 3, or 5Q minus P in bracket whole upon q equals to root 3. Here 5q minus p upon q is rational number. Therefore root 3 is also rational, which is a contradiction because as we know root 3 is irrational. Thus our assumption is wrong. Therefore 5 minus root 3 is irrational. This proves our theorem. Now we will do the next question. Prove that 1 by root 2 is irrational. This question will be proved by contradiction method. So let 1 by root 2 be a rational number. Then 1 by root 2 can be written as p by q, where p and q are integers and co-prime. Here first we will multiply numerator and denominator of 1 by root 2 by root 2 to rationalize the denominator, or the equation can be written as root 2 equals to 2p upon q. Here 2p upon q is rational. Therefore root 2 is also rational, which is a contradiction as we know that root 2 is an irrational number. Thus our assumption is wrong. Therefore 1 by root 2 is irrational. This proves the question here. Next topic we are going to discuss here is decimal expansion of real numbers. Let us find the decimal expansion of some of the real numbers here. When we divide 5 by 8, we obtain the quotient 0.625 and the remainder is 0. So here we have to note that when the remainder is 0 and the decimal expansion terminates with a finite number of terms, such type of decimal expansion is called terminating decimal expansion. And when we divide 5 by 9, the quotient obtained is 0.555, which keeps on repeating. So here we don't find the remainder 0. So we should note that when the remainder is not 0 and the quotient keeps on repeating, such type of decimal expansion is called as non-terminating recurring decimal expansion. Now just note down that terminating decimal expansion and non-terminating recurring decimal expansion, they can be converted in the form of p by q, so they are called as rational numbers. Let us see some more examples. 5 upon 8 can be written as 5 upon 2 to the power 3, which is equal to 0.625. 13 by 25 equals to 13 by 5 to the power 2, which is equal to 0.52. So in these two examples we saw that the denominators are having the factors 2 or 5. From the above examples we conclude that the rational number p by q will have terminating decimal expansion if the factors of the denominator q is of the form 2 to the power m multiplied by 5 to the power n, where m and n are whole numbers. Now let us see one more example here, that is 5 by 9. So this is equal to 5 by 3 square, which is equal to 0.555. So here we saw that the decimal part is repeating and the denominator is not having either 2 or 5 as factors. So from the above example we conclude that the rational number p by q will have non-terminating recurring decimal expansion if the factors of the denominator q is not of the form 2 to the power m into 5 to the power n, where m and n are whole numbers, or we can say m and n are non-negative integers. Now let's see the numbers 0.10, 1001, 0001 and so on. So here neither the decimal terminates with finite number nor the decimal part is repeating. So such type of decimal expansion are called as non-terminating non-recurring decimal expansion, and non-terminating non-recurring decimal expansions cannot be converted in the form of p by q, so they are called as irrational numbers. Now we have some theorems related to the facts that we have studied just now about terminating and non-terminating recurring decimal expansions that we will see now. Let us see what theorem 1.5 says. Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form of p by q, where p and q are co-primes and the prime factorization of q is of the form 2 to the power m into 5 to the power n, where m and n are non-negative integers. Now theorem 1.6. Let x is equal to p by q be a rational number such that the prime factorization of q is of the form 2 to the power m into 5 to the power n, where m and n are non-negative integers. Then x has a decimal expansion which terminates. Now let us see what theorem 1.7 says. Let x is equal to p by q be a rational number where p and q are co-primes, such that the prime factorization of q is not of the form 2 to the power m into 5 to the power n, where m and n are non-negative integers. Then x has a decimal expansion which is non-terminating recurring. Now let us solve the following question without actually performing the long division. State whether the following rational numbers will have a terminating decimal expansion or non-terminating recurring decimal expansion. Let us find the decimal expansion of 13 by 3125. To do so, we will factorize the denominator first. After factorizing, we get 13 upon 3125 is equal to 13 upon 5 to the power 5. Since the denominator is of the form 2 to the power m multiplied by 5 to the power n, that is 3125 is equal to 2 to the power 0 into 5 to the power 5. Since there is no factor 2, so we can write 2 to the power 0 here. Therefore, it has terminating decimal expansion. Now you all have to do some home assignment. Solve exercise 1.3 and 1.4 of NCERT textbook. Thank you everyone for watching this video. Now we will meet in another class.